everyone, and welcome to Keeping Tabs on Chemistry. In this video, we're going to be discussing calorimetry. Now, calorimetry is a new term. This is a scientific word meaning heat calculations, specifically the heat calculations involved with temperature changes. Now, so far, we have only used units of joules to describe energy, because that is the SI unit for energy. However, calories, CAL, are another commonly used unit for energy. 1 calorie is equal to 4.18 joules, and you're going to be seeing that number quite frequently. And there is a reason why we decided to use 4.18 to redefine 1 calorie. Now you can convert between calories and joules using dimensional analysis. Now some of you might see the word calorie now. Oh yeah, I know calories. I see it on the back of my food products in the nutritional information. The calories you see in nutritional information tables are actually kilocalories, and it's sneaky. The way that they represent it on this packaging is with a capitalized C, calories. So this means that consuming the suggested 2,000 quote-unquote calories a day, you're actually aiming to consume 2 million real calories every single day. It doesn't actually change anything about how much you're eating and the packaging, and we know, and the 2,000 every day. It's just a difference of scale and how it makes you think, oh, it's just 2,000. It's actually quite a lot more for our bodies to run each day. Now we have to define another value as well, called specific heat. Specific heat is represented by an uppercase C or sometimes an uppercase C with a subscript P. Specific heat is the amount of energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius, or the equivalent 1 Kelvin. Now, how is it that 1 degree Celsius and 1 Kelvin? Kelvin and degree Celsius, although the values are different, 1 degree Celsius is equivalent to 1 degree, well, not degree, but 1 Kelvin. So a change in 1 degree Celsius is the same as 1 Kelvin, even though the absolute magnitude of the values are different. Now, the units of specific heat are joules per gram degree Celsius. This is the amount of energy per gram per degree Celsius you're raising the temperature by. Now, it doesn't have to be in joules, it could be calories per gram degree Celsius as well. Now, the specific heat of water is commonly known, and you are going to have to know it as well. It is 4.18 joules per gram degree Celsius. Remember that number? This means that the specific heat of water is 1 calorie per gram degree Celsius. That is why we redefined calories to be 4.18 joules. It's because of water. Now, the equation that you're going to use to calculate the energy needed to raise temperature is affectionately known amongst chemists as MCAT. If you're not familiar with what the MCAT is, that stands for the Medical College Aptitude Test. It's the same thing as the SAT, but for medical college instead of general university. So Q. Q is just the change in heat or energy. Sometimes we've seen this lowercase q as a delta H, sometimes I've written it out as just energy. It's just another form of chemical notation. The M in this case stands for mass, C is the specific heat, and delta T is the change in temperature. How do you calculate a delta T? Well, it's final minus initial, any change really. So let's look at what some of these questions might look like. In example 1, it says how much energy is required to raise the temperature of 250 grams of water from 18 degrees Celsius to 78.5 degrees Celsius. The question is asking me for energy. That means it wants Q. So I have to make sure I have M, C, and delta T. The mass is 250 grams. Great. Specific heat. It doesn't tell me that outright, but it does tell me that it's water. And the specific heat capacity of water is 4.18 joules per gram degree Celsius. Now for delta T, it gives me a range of temperatures. It goes from 18 to 78.5. Well, to find the change, I do final minus initial. I started at 18, I ended at 78.5. So when I go to solve for Q, I've got the mass 250, the specific heat 4.18, and then the final 78.5 minus the initial 18. I'm going to start by solving inside the parentheses here, 60.5 degrees Celsius, and then multiplying these three values together, I get 63,313.3. That's a lot. We're going to look at sig figs. Considering sig figs, I had 4 significant figures here, 3 significant figures here, and 3 here. Remember, going from here to here, right? Subtraction goes by the least number of decimal places. Both of these had 1 decimal place, so when I input it here, it had 1 decimal place. So I'm going to consider this number with 3 sig figs in my final calculation. So between 4, 3, and 3, I need to shorten this down to 3 sig figs. So from the first 3, this does not round up. These become zeros, and I knock off any decimals. So it becomes 63,300 joules. Hold on, where did I get joules from? Well, if you look here, the only place I'm getting energy from is my specific heat. The specific heat is in units of joules, so my answer will be in units of joules. Now, it doesn't actually specify I needed joules. I could have done this in calories as well. This just would have been 1 calorie per gram degrees Celsius. Example number 2. We're going to make it a little harder. It says a 4-gram sample of glass was heated from 274 Kelvin to 314 Kelvin and was found to have absorbed 32 joules of energy. What is the specific heat of this type of glass in joules per gram degrees Celsius? Now that's important because it means I don't have to convert this to calories. I can leave it as joules to get my answer in joules. So I need C, I have Q, I have mass, I'm looking for this, and I can find my delta T. So 32 joules of heat energy. Notice it says absorbed. That means this is going to stay positive. My 4 grams, I'm going to have X for C and then 314 minus 274. I'll start by solving my parentheses and multiplying by 4. I divide both sides by 160, and I find X to be 0.20 joules per gram degrees Celsius. Notice these all had 2 sig figs, so my answer has 2 sig figs. In example number 3, it says 50 kilojoules of energy was used to heat 250 grams of water to a final temperature of 95 degrees Celsius. What was the initial temperature of the water? This is a slightly more complicated problem because we need to put our variable inside of delta T. So I have my Q, I have my mass, I know the specific heat of water, and I can separate out the delta T into final minus initial. Because I have final, I want to know this initial temperature Ti, right? F for final, I for initial. Now the specific heat capacity of water is 4.18 joules per gram degrees Celsius. Now some of you might gloss right over that fact and go straight to plugging things in, but there's a problem. My specific heat is in joules, but my energy is in kilojoules. I need to convert one of these, either kilojoules to joules or joules to kilojoules. It's much easier to deal with that unit than try to deal within that unit. So down in the corner here, I've got 50 kilojoules. 1 kilojoule is 1,000 joules. I went ahead and converted it to scientific notation. I've got 5 times 10 to the 4th joules, or 1, 2, 3, 4, 50, 50,000? 50,000. So my Q here is 5 times 10 to the 4th. My mass is 250 grams. My specific heat is 4.18. My final temperature is 95. My initial is X. Right, when I go to solve this, I'm going to start by multiplying these together, get 1045. Then I'm going to want to isolate this on one side, so I divide both sides by 1045. I end up getting 47.8 equals the 95 minus X. Right. I'm going to subtract out 95, change the sign, however you want to do it, solve for X, you get 47.2 degrees Celsius. And that is my final answer. Okay, so far in this unit, we've talked about specific heat and then molar heat, or heat of fusion / heat of vaporization. So we now have 2 different types of heat calculations. During a phase change, we're dealing with molar heat. Q is equal to the molar heat in either kilojoules per mole or kilojoules per gram times moles or grams depending on what units we have. The heat of fusion or vaporization is the energy needed to change state, to undergo a phase change. Now, as temperature increases, you're using a different calculation. In that case, Q equals MCAT using specific heat, which is the joules per gram degree Celsius. Specific heat is the heat energy needed to raise the temperature within one state. So, when you're looking at heat calculations, you have a decision to make on which equation you're going to use. Look for words that tell you whether or not you are having a phase change, if you're going from liquid to solid, or if it gives you molar heat, versus if you have a temperature increase. If you have anything in degrees Celsius or in Kelvin, you're dealing with temperature increase and therefore MCAT. So you have to be careful between these two to make sure you're using the right equation with the right values. Now, that concludes our lesson on calorimetry and heat calculations. I'll see you next time.